Right. Uh, we'll just go through a quick recap of the language model, something like what we have seen. So we were something telling about a language model. Basically, it's a statistical model that assigns some probability to words and sentences, right? And what we have done is that some of the applications that we have seen is like guessing the next word w in a sentence given all previous history or previous words. For example, like that we can say is that I am a dash. Okay, I am a dash. What's the probability that the next word is um elephant? Okay, or what is the next word is boy? So what the probability? So given here, the probability that probability of boy given I am a is greater than probability of uh, elephant given I am a, right? So this is how we are interested in some applications, right? So what we can do is that we are also often interested in the probability that our model assigns to a full sentence w, uh, which is made of some sequence of words w1 w2 w3 like that, uh, with some sequence. So we are mostly interested in that, right? That a sequence should be that sequence, or that sequence should give us high probability. Okay. Okay. What we try to do is that we would like to model or assign some probabilities to sentences that are basically spoken in our real life and which are syntactically correct. So if you simply see a unigram model, then probability of w equal to w1 into the probability of w2 into w into probability of w3 into probability of w4 like that. Okay, probability of some wn like that we can go through. And if it is a bigram model, probability of w is equal to what we try to give it, probability of w1 into probability of w2 given w1 into probability of w3 given w2 into like that probability of at last probability of wn given wn minus 1. And if you say it is like a n gram, then probability of w is equal to probability of w1 into probability of w2 given w1 into probability of w3 given w2 comma w1 into like that probability of wn given probability of wn minus 1 comma probability of wn minus 2 like that we will see. Okay, if it is n gram up to n minus 1 items we try to see the sequence. Okay, uh, so we are interested in finding out like what is the next word like that. So whatever may be, how do we evaluate these language models, whether it is bigram is better, trigram is better, unigram is better, or like quadgram, pentagram, 6 gram, 7 gram, 8 gram, or any other language modeling methods. Okay, how do we try to find out? So this we can say that like perplexity is one of the evaluation metrics for language models. But why do we use it basically here? See, like we can use two different approaches to evaluate or compare the two language models. One is the extrinsic evaluation. So extrinsic evaluation involves the models by employing or deploying them in the actual task. So during that time, maybe like when you are conversion or like conversating with one language to another language, or like translating from one language to another language. In that case, like the words that you, I am a boy, मैं एक लड़का हूँ. Okay, I, मैं, a, एक, for example. Okay, a, I am. So may are you going to get the exact conversation, or like are you going to get it? See, sometimes as I said you earlier that languages, some of the languages it happens like a subject and subject object, or subject and predicate, or after this subject, then you try to get some verb, or verbs first, then you get it, or subject and object or object and
Sir, are you
subject.
changing the slides?
No, 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 I did not change any slide. Okay, till now.
Okay.
Okay, fine. So this way there may be many things that may be available. So in that case what happens is that you do not get. So if you are able to evaluate that exactly and then get such type of evaluations, you generally use it your accuracy, or maybe like the F measure using precision, recall, all this, right? But for intrinsic evaluation, so intrinsic evaluation, or we try to find out some metric to evaluate the language model itself. So this perplexity is an intrinsic evaluation method. Okay, so what we can try to do is that a good language will assign high probabilities to valid sentences and low probabilities to invalid sentences. It means that if a language is syntactically correct for a language, the probability will be high. If it is syntactically not correct, or less usage in that particular language, less usage of those particular sequences in that language, then the probability will be less. So given a corpus to test some sentences, for example sentences SI, let us assume that there are m sentences like that. So we want to compute the corpus probability with respect to the language model over all the words in the corpus. So it is given as log product of I equal to 1 to m probability of those sentences, or it can be given as summation of I equal to 1 to m log p of Si, right? Now a good language model uh, should have what should be, how do we evaluate that as a good language model? Okay, so as given like the equation earlier, the top equation, so taking an average of all the words in that corpus, we try to give it as like L equal to 1 by m summation of I equal to 1 to m log p of Si, and we try to give it perplexity as a measure like 2 power minus L. Okay, this is the basic formula that is used. How do we perplexity? If you see anything perplexity, it means that it is the how much that word gives us confusion, or that particular sentence gives us confusion. Perplexity means confusion. Okay, if there is more confusion, it means that the probability is more confusion, probability is less confusion, it means that probability is high. It means that probability is high means the sentence is correct, syntactically correct. Okay, the nearness to correctness, okay, it is near to correctness, that's why the probability will be high. When probability will be high, it means that you can easily understand that the confusion is less. Okay, there will be less confusion, it means that the perplexity will be low. So let's say we have a language model which predicts each word randomly from the corpus of V vocabulary of n size words. Okay, so it means that probability of Wi equal to 1 by n. What is the perplexity in this case? Okay, so if you see uh, L equal to given earlier 1 by m sigma I equal to 1 to m log p of Si. So the perplexity is to be taken as 2 power minus L. So here L is nothing but log 1 by n. Okay, log n by n. So definitely what will be the perplexity here? The perplexity here is n. Now one more thing like we can also say is that like this perplexity is a measure of branching factor, or like how many ways it can be thought, or like how what is the confusion that it can create, that is what is to be understood here. Okay, so the typical values of perplexity given by the the Goodman, Rich and Goodman, they have conducted the experiment, and they have given for the sentence a bit of progress in language modeling. That is the article. Okay, a bit of progress in language modeling. There they used like something around the vocabulary size is 50,000, and they have given like for trigrams. For trigrams, the perplexity is 74. I hope you understand what is a trigram here. So q of xi given xi minus 2 and xi minus 1, right? Combination of these three words, the perplexity is 74. And for bigrams, the perplexity q of xi given xi minus 1, 2, two words, right? The perplexity is 137. And you see for unigrams, the perplexity is 955 here, 955. Okay, it means that existence of single words. Okay, single words, the perplexity is 955, whereas for bigrams it was 137, for trigrams it was 74. What would be the probably like whether it will be less or more for a quadgram, pentagram? Yes, yes, it will be less or more. The perplexity will be less or
Less.
more for a quadgram.
Less.
It will be less. The reason is very simple, because when a sequence of sentences is already available, suppose I say simply, let us see about unigrams. I, what is the next word that I am going to give? So here there is a total confusion, right? I, okay, I, then what will be there? There can be any number of words followed by I. Okay, for bigrams, for example, I am, okay, he is telling I am, so the sequence again comes little bit less again. After am, I am is there, so definitely there will be some words, only very few, maybe like some not as unigram words followed, one the word I followed by any number of words like that, but it will be still, it will be less, right? Little bit of confusion is less. So if it is trigrams, I am A. So it means that still I am A. Okay. Now, who is this person? Only that things you need to put up. Either maybe like some nouns, noun words, or proper nouns, or different types of nouns that you need to give it. I am A of, you cannot give it like that. So definitely no conjunction, interjunction things and all may come into picture like that. So definitely the perplexity will be more or less. Okay, it is because of the high probability of those occurrence. Okay, so that's why a 4 gram thing will be the perplexity for a 4 gram will be less, and for a 5 gram, for 6 gram, 7 gram, it will be more or less. Okay, so but one of the major thing that we need to see in language modeling is dealing with zeros. Dealing with zeros means like a occurrence of those words will be nullified or zero, it will be zero, right? Or those particular occurrences are not available in the literature. So n-gram only works well for word prediction if the test corpus looks like the training corpus. It means that it is available, the data is available. Okay, if it is not available, then how does this n-gram model work? But in real life it doesn't, it often doesn't, right? It is not like the same. It is not like the same that you have learned all the words in a particular language, but do you think that expect that how you learned the vocabulary and the sequence of the vocabulary that you have learned, will it occur in the same way? It may not. Some words you must have not known also. Okay, so we need to train robust models that generalize, and one kind of generalization that is needed is dealing with zeros. Dealing with zeros means things that don't ever occur in the training set, but they occur in the test set. So as I said you, like those particular sequence of words do not occur in the training set. okay, when training the data, but they ultimately occur in the testing set. Like, say for example, you see the training set is here, okay, denied the allegations, denied the report, denied the claims, denied the request, like that. And in the test data set, you, if you see here, denied the offer, that is not available in training. Denied the offer, denied the loan, that is not available in the training data set, right? So suppose it is given probability of offer. What is the probability of offer given denied the, for this trigram, okay, what is the probability now then? So it was not available in the training set. So definitely it should be, it will be 0. But it need to be handled properly. Okay, these things are to be handled, because if you see denied the probability of maybe like allegation, report, claim, request, all these words will be given having some probability. But offer has no probability, because there is no word available there. So how can you assign some probability there? So it means that it should be a 0 probability. If 0 probability, but actually it is a correct sentence. Syntactically they are correct. Denied the loan, denied the offer. Okay, these are the right sentences. So how can you neglect it? So how to overcome this one basically? So one of the methods that can be used is a smoothing method. Uh, I hope my slides are in syncing. No problem. You can
Yes,
see
sir.
my slides is smoothing.
Yes, sir.
Okay, fine. So when we have sparse statistics, it means that more number of zeros are also available there. So you see here, probability of W given denied the, what would be the next words like allegation, report, claims, request, those have been trained. It is seen in the training and it is available, right? Now, so total 7 words are available like that, or the training count is 7 here. Row bigram count or maybe like trigram count is 7 here. And if you see here, this is, we are having some count for allegation, for report, for claims, for request, but denied the attack, okay, we do not have any value. Denied the man, we do not have any value. Denied the outcome, we do not have any value for this one, okay. The value here is 0. So what we can try to do is that from this, okay, from this, can we steal some probability? Okay, some probability can be stolen from this existing words, okay, existing counts, and then assigned to attack, man, okay, man, and outcome. So like this, 0 occurrence words. So here if you see this one, stealing simply 0.5 probability, okay, 0.5, 0.5 probability has been stolen from each of the existing counts, or count, from count only 0.5, suppose we are negating it, okay. So here from 3.5 is being negated, and then 2.5, here 2, and it is 1.5, zero point 0.5 and zero point 0.5. So the other, so remaining words, everything total, they will have a count of 2. So this one, stealing from the existing counts and then assigning it to the other counts, assigning it to 0 occurrence counts, okay. Another method that is can be used is like add one estimation, or like add one estimate. It is like it is also called as this Laplace smoothing, okay. So we add each bigram one more time, so one count is being added extra, that is just add 1 to all the counts. So if you see the maximum likelihood estimate, conventionally that we use as for the probability here, maximum likelihood estimate in the language modeling, when we use n for the conventional n-gram model, what we were using is the maximum likelihood probability of wi given wi minus 1 equal to the count of wi minus 1 comma wi, sequence of occurring of these two words combinedly, by the count of wi minus 1, okay, occurrence of the previous word. or one the earlier word. So for this we can give a add one estimate as simply adding, okay, adding by 1. So here you see add one estimate or add one probability of wi given wi minus 1 equal to count of wi minus 1 followed by wi plus 1. Okay, the combination of occurrence of these two words wi minus 1 and wi, the count of this bigram occurrence plus 1 divided by the count of occurrence of wi minus 1 plus the vocabulary size v. Yes, okay. So if you see here earlier from the Reuters data set, the Laplace smoothed bigram counts, if you see here uh, on the top table, you see that this was the likelihood simply count. The bigram counts of this combination of these two words, okay, two words, bigram counts. And here you see the Laplace smoothed bigram counts. You simply added one more, like here it is 60 and here it is 61. Here it is 0. You see here it is 0. Okay. Here it is 1. Okay. You added simply. Here 0, 0, 0 and 1, 1, 1. Here it was 1 and here you added just one more. 1 plus 1, 2. And here 0, 0. It is 1, 1. So like this, just only one increment has been done to this one. This is add one estimate or Laplace smoothed estimate. Now the Laplace smoothed bigrams can be given. The probability value can be given with the same the formula like this. So P of, you see here my mouse is not working properly. Okay. P of Wi is Wn given Wn minus 1 equal to the count of Wn minus 1 Wn plus 1 by count of Wn minus 1 plus the vocabulary size. Okay, please remember this. Okay, you see here the reconstituted counts. If you see, the reconstituted counts, so uh, the count of Wn minus 1 Wn equal to the count of Wn minus 1 Wn plus 1 into count of Wn minus 1 by count of Wn minus 1 plus the vocabulary. Okay, this is simply you need to know the formulas. Like earlier, this is the Laplace to smooth bigram values, and then later you have to find know the reconstituted counts. So if you compare with raw bigram counts, simply raw bigram counts and then reconstituted counts, you can see that what would be the values. If you see here, this is a sparse matrix. Okay, right? There are so many occurrences of zeros are available here. But here, if you see the second matrix, okay, this matrix, if you see here, in this matrix, there is no zero occurrences. Okay, we are trying to overcome the zero occurrence problem, right? This is one of the method. Okay, now similar to add one estimate, what we can do is that add case estimate also can be there, or add case smoothing can be there. So for that, it can be given like this as P of Wn given Wn minus 1 equal to, here like this is conventionally for add one estimate. This particular formula is for add one estimate, right? So what we try to do is that instead of plus 1, we try to give it plus k. Okay, we try to give it plus k. Plus 1 can be replaced by plus k, and this v vocabulary 1 into v. So here k into v. Okay, this is k into v. You need to put up. This is the same formula provided here, plus k, and this is kv. Now add one estimate or add k estimate is very good for this text classification. Mostly in the domains where the number of zeros are not so huge. Otherwise, what we can try to do is that we can go with some other methods. We can go with this interpolation method, backoff method, web scale language models. Like that, we can go with different methods. So this backoff and interpolation method, if you see, this backoff method is a very simple technique. First of all, you use a trigram if you have non-zero counts. If non-zero counts are there, it means that if you have non-zero counts, okay, or if you have zero counts more, then what you can try to do is that just back off with the trigram and then go with bigram. Still, if the problem is persisting, then back off with the bigram and go with the unigram model. And sometimes some methods of these which use the back off technique, they usually combine with the discounting methods. What interpolation method do is that they mix the combination of unigram, bigram and trigram. So if we see here, like p cap, okay, this is for interpolation we are trying to give. P cap of wn given wn minus 1, wn minus 2 can be given as lambda 1. So few things, whatever bigram, trigram you can do it. Trigrams, whatever bigrams you can do it, and whatever unigrams you can do it. But they need to be for bigram lambda 1, lambda 2, lambda 3, they need to be multiplied with. Okay, but one thing, so these probabilities or these lambda values should sum to 1. Okay, the summation of all these lambda values, lambda 1, lambda 2, lambda 3 should be 1. Okay, now how to set these lambda values basically? So here we try to use the held out data set or validation data set. So we are having the training, validation data set, test data set. So you choose lambdas to maximize the probability of this held out data. So fix the n-gram probabilities in the process of training. Then search for lambdas. So you need to do so many experiments then in that. The validation, see, that is what you try to do it, right? When you are trying to do maybe like some cross validation or something, what is the best value that is good? Okay, how many threefold validation, fourfold validation, fivefold validation. So you go on doing like that, right? So you try to find out like that only. You try to find out the best value for lambda that gives the largest probability to the held out data set. So you try to get it like log p of w1, w2, w3 like the wn given m, the maximized lambda. Okay, the summation summed and maximized lambda is equal to sum of I log pm maximized probability of wi given wi minus 1. Another method you try to use it is like along with this is the discounting method. What is this discounting method? Discounting method is like the, see in the first like example, the followed by dog is 15 times it has occurred. The dog, the woman 11 times. The count is 11. The man 10 times. The park 5 times. The job, the telescope, the manual, the afternoon, the country, the street, and the cat. Okay, like this, how many times it has occurred like this, we try to give it. For this, how we try to do the discounting is like we try to extract, okay, we try to extract some value as such like this. So for example, the count of the is 48. So you try to make it like 15 by 48, 11 by 48. This way, okay, you try to discount some value for the particular bigrams, and so discounted bigram is the original bigram count minus 0.5. For example, you can do like this, or so the new estimate for the non-zero bigrams, it can be for this non-zero bigrams, okay, the cat, for example. How do you calculate for the cat like that? So we have some missing probability mass. So here if you see in this case, okay, how much you steal, like 1 minus this total is 43, okay, maybe like 14.5, this values, everything is 43 divided by 48, that equal to 5 by 48. So this value, this 5 by 48 can be assigned, this can be discounted, okay, this can be discounted, and then this value 5 by 48 can be assigned to all the non-zero elements now, non-zero or sorry, zero bigrams, okay. And another method that is basically usually used is like, or like the good Turing discount method, that is like a good Turing discount method is like given here. uh, this we call this one also like maximum likelihood estimate proposed by this good and Turing, okay. If you see this, it is like DA, the discount of the word A, okay, can be given as, or event occurring A times, okay. This is A occurring of A times, this A times can be given as DA is equal to A plus 1, the count A plus 1 by A into CA, or like DA can be calculated in this way, okay. This is the direct computation if, okay, if it is between 1 and k is the cutoff basically, okay, here, or like what you try to give is that some value where you wanted to make a cutoff, okay, cutoff value. And for if it is greater than k, if this A is greater than k, then you put it 1. But here also we have a problem of, what about if it is A is zero occurrence, okay, for zero occurrence this is not given here. So what we try to do is that we use CAT's backoff models. CAT's backoff model is the same like that of the backoff model that we have seen earlier. So for bigram model, it means that few bigrams, few trigrams, okay, sorry, few trigrams, few bigrams, unigrams, like that. See, generally a language model, they do not go with 4 gram, 5 gram, 6 gram and all. To a maximum, okay, in any language you try to go at maximum is like 3 grams or trigrams, okay, bigrams, trigrams, that is the mostly used things, okay. So for a bigram model, you define two sets, A of wi minus 1 and B of wi minus 1. A of wi minus 1 is count of wi minus 1 comma w is greater than 0 here, okay. This count value is greater than 0 and this count value is equal to 0, A and B. So you give Katz's backoff model. Katz's backoff wi given wi minus 1 is like, if A of wi, it means that it occurs greater than 0 times, then you give this formula, basically you apply this formula and you get the substitute the value. If it belongs to 0, it means that if wi equal to 0, okay, then you apply basically this particular formula, okay, this particular formula. Whereas alpha wi minus 1 is given with this particular formula, again 1 minus summation of w belong to A of wi minus 1 count of wi minus 1 comma combination of the bigrams by combination of that count of that unigrams. Okay, wi minus 1. Now Kurt's back of model, using Kurt's back of model you can do like you can also estimate, that is given for a trigram model. First define two sets. Okay, first define two sets, wi minus 1 like this, wi minus 2, wi minus 1 like this. Then later again you can define with again two sets. Okay, like wi minus 1 and then wi, you can yes, you are trying to give it wi minus 2 comma wi minus 1 and wi minus 2 comma wi minus 1, because you are trying to you are now you are interested in wi. Okay, so combination of these three makes a trigram. Okay, so this way you try to find out, again you are trying to give it like if this occurs. Okay, you are trying to give a set with wi minus 2 followed by, or wi minus 1 followed by wi minus 2. Okay, with the existence of greater than 0 and existence of equal to 0. Then same like that what we have seen earlier formula, same here also you apply the same, provided with its occurrence. Okay, whether it is more than one occurrence, more than zero occurrence, or zero occurrence. And the for alpha formula here, alpha wi minus 2 comma wi minus 1 is given as like this, 1 minus sigma w belongs to a of, or it means that more than one's occurrence should be there. Then in that case count of these three. Okay, this trigram divided by count of this bigram. Fine. Then Brands et al. Okay, some researchers along with Brand in 2007 show that with very large language models, a much simpler language algorithm may be sufficient. And this algorithm is called sometimes, like we trying to give it this simple algorithm as stupid back off, or stupid back off method. Okay, stupid back off gives us the idea of trying to make the language model a true probability distribution, and there is no discounting of the higher order probabilities. If a higher order n-gram has a 0 counts, so we simply back off to a lower order n-gram weighed by a fixed context independent weights. So here what we are trying to do, we do not have in n-gram models, web scale in n-gram model, we do not have a discounting method. We have a back off method. Okay, this algorithm does not produce a probability distribution. Okay, so stupid back off method is given with this formula, no discounting, and just use the relative frequencies only for that language. Okay, this is the formula, it is given. This is basically an estimate which is like a with a statistical calculation, 0.4 s of wi given w I minus k plus 2. Okay, where s of wi is given as like the count of the wi by n. If it is greater than 0, you need to follow this formula, above formula. If it is 0, okay, then you need to follow this particular strategy. So n-gram summary, if you see, like add one estimate or add one smoothing is okay for text generation and not for language modeling. The most used method is basically Nizar-Ney method, extended interpolated Nizar-Ney method. We also have another method like that, or like good Turing discounting. But for very large n-gram like the web, we can simply use it, the stupid back off method. How to deal basically with unknown words? This is another challenging thing. So for time being, simply what we try to use it, that is like, suppose we are having a V is fixed. If it is closed vocabulary, we do not have any problem. But if it is out of vocabulary, OOV words, what we try to do is that we try to create an unknown word token, UNK, and training of this unknown word token probabilities can be done. So what we how we try to do it, find most infrequent words, a few of them, and replace them with these unknown words. Now we train with its probability like a normal word. So during the testing time, use these unknown probabilities for any word which do not come in the training corpus. Fine. Then what we can have is that, like advanced models, we can work with language modeling tasks. So we with this neural language modeling tasks. So conventional, if you see a language modeling task, the input that is given is the sequence of words, right? X1, X2, X3, X4, X5, like that up to Xt. The output is the probability distribution of next word P of X t plus 1 given P of Xt, like that, X1. So for the what will be the t plus 1 word? Probability of t plus 1 word. That is what we are interested in. So we can use, okay, the neural network and recurrent neural network mostly for the sequential data and all. We will try to use the recurrent neural networks, which can be used for learning the probability distribution over occurrence of words in a sentence. So nowadays, more advanced methods are also used, like for overcoming, like for long dependency and all. We can use it, that LSTMs, or maybe like we can use attention mechanisms. We can also use bidirectional encoders, okay, but encoders and transformers, like that, combined together we can use it. So these are the neural language models that can be used, okay, and we'll discuss all those language models, neural network models separately, maybe like next lectures and all. We'll try to use it, okay, we'll try to discuss about them. So we need to discuss about the neural networks. We need to discuss about the recurrent neural networks, about the LSTMs or GRU, okay. Then we need to discuss about the transformers, encoders, okay, and the but we can discuss about that one. Mm, so some limitations and challenges of the language model, you can see that simple models basically fail to capture the deep structure or the intention or thought behind them, right? This is very much sure. It is difficult to capture. Difficulty in sentence level issues like the subject verb agreement, subject number agreement, semantic coherences, sentence sequencing, and relevance. So all this we may fail with the simple models. uh, Existing language models. So extremely sensitive to changes in the style or topic or genre of the text, which they are basically trained. So see, that's why I say that, like the sequence, the genre of movies that you see, for example, you train for English movie, it may not be true with respect to your regional movies. Okay, the genre may change, the taste. So we have some advanced language based models. We use the discriminative models, parsing based models, neural language models, some caching models, like which is given here. So you try to keep up the cached words, recently used words. That is what you are, that is the formula, that is the given formula, which means that, okay, the recently used words are more likely to appear with that assumption. So you can use some caching models also, can be used. So the summary of the evaluation of the language models is that modeling is needed to deal with the complexities, and we use the probabilistic language models. Uh, like a statistical model, using the statistical models like n-grams, or like neural models like RNN also can be used. And some of the challenges are, like as I said earlier, long term word dependencies and semantic relevance is all not available. Basically, we have got sentence level issues where the meaning gets changed, and dealing with the occurrences words, okay, unknown occurrences of the words, like that also, okay, there are problems. So the lecture is done. If you want ask some doubts, you can ask, otherwise we can wind up. I'm just stopping the recording, okay.